Okay, let's take a peeky pie at example 3, which says use tables of values and a graph to solve this system. Okay, so I'm going to kind of condense this table of values instead of making two separate ones for these two different lines. I'm going to call this the first equation, the y from the first equation, and I'm going to call this y2. So this is my first equation's y value, and this is my second equation's y, and I'm going to fill it out simultaneously. Okay. If x is 0, 2 by 0 is 2. I'm sorry, is 0. 2 zeros is 0, plus y equals 2. So y is just 2. Here, if x is 0, negative 2 by 0, or negative 2 zeros, is still 0. So that means y2 is 6. Okay, let's do this again. They are not equal yet, so it's not matchy-matchy. If x is 1, two ones, or 2 times 1 is 2. 2 plus y is 2, so y must be 0. But I feel like I just keep solving this equation, and that's getting like hard to keep track of everything. So maybe what we could do is rearrange this, subtract 2x from both sides, and I feel like that's going to make our life a little bit easier in terms of computations. Same here. So this, we would add 2x to both sides. Okay, got it. So if I plug in 1, I get 2 minus 2. That's 0. If I plug in 1 here, I have 6 plus 2, that's 8. Got it. Let's plug in 2. 2 minus 4 is negative 2. And 6 plus, 2 by 2 is 4. 6 plus 4 is 10. Oh boy, I feel like these are getting actually further apart from being equal. So maybe I should dip into the negatives? Okay, let's give that a shot. All right, negative 2 by negative 1 is positive 2. 2 plus 2 is 4. And in the second equation, 2 by negative 1 is negative 2. So 6 minus 2, oh my gosh. Lovely. So we just found where they match. So we found our solution when x is negative 1. Both of the y values are 4. So in this equation, when x equals negative 1, y equals 4. And in this equation, when x equals negative 1, y equals 4. So we have found it. That's nice. And then it says also a graph. Okay, so I'm going to go ahead, put it on here. Go to y equals, put in, let's see, 2 minus 2x for the first one, and 6 plus 2x for the second one. And I'm going to go zoom, standard, enter, and let's see what kind of graph we get. All right, I see it. Ooh, look it. When x is negative 1, they meet at 1, 2, 3, 4, la-di-da. It agrees with us. Okay, so, we graphed both of these equations, and we got a picture that looked like, let's see, this one looked like this, and the red one looked like that, and they met right about there. and that was when x equals -1, y equals 4. So we get the solution, -1, 4. Got it. Yay! Oopsie, I read the wrong way. Okay. Is the coordinate pair 0, 2 a solution to this system? Well, a solution to the system is the two values, the x and the y, and these make both equations actually true. Okay, so let's test that out. If we put 0 in for the first equation, so put 0 where the x is and put 2 where the y is. Well, 2 by 0 is 0, plus 2 makes 2. And does that satisfy the equation? Yes. So it really is actually true. And now we'll check the second one. So that would read -2 by 0 plus 2 equals 6. Well, -2 zeros, or 0, -2 times is nothing. Nothing plus 2 is 2. So sadly, no. Okay, so is this a solution to the system? No, because it has to make both equations true, and it didn't make the second one true. Okay, and then it says check the solution you came up with for this system. And we came up with -1, 4. Okay, 2 by -1 plus 4 equals 2, question mark. -2 plus 4 is equal to 2, check. And let's see, -2 by -1 plus 4 equals 6. Negative 2 times -1 is +2. 2 plus 4 makes 6. Yes. It worked in both. It made both equations actually true. Rewrite the system, but with the equations in y equals mx plus b form. Okay, so actually we had to do that in order to graph this. So we might as well just copy down what we had written here. Okay, so our system looks like y equals, oh, but it says mx plus v form, so I need to put that first, I guess. -2x plus 2. And the second equation would read +2x plus 6. Okay, so here's our system written in y equals mx plus b form. Solve the system using an equation instead of a table or a graph. So instead of using this table and instead of using this graph, use an equation. Okay, well here's the thing. If the y has to be the same for both of these, then these two must be equal. So here's what I mean. Okay. If y equals -2x plus 2 in the first one, and also this y is equal to 2x plus 6, then I can replace it. Because they have to be equal. In order for it to work in both, they have to be the same amount. This y has to be the same amount as this y, otherwise it'll disagree. So here's our equation, and now let's solve it. Okay, well, I'm going to add 2 x's so that all of my x's are on one side. And remember the, what was it? The additive property of equality means if you start with equals and you add or subtract the same amount, you still have equals. So I'm going to add 2 x's to both sides. That leaves me with 4x plus 6 on the left side of the equals, because these are like units and like terms. And over here, this would go away. There would be -2 x's plus 2 x's, so no x's, but I would still have 2. Okay, that means, let's see, whatever this is must be -4, because -4 plus 6 makes 2. So that means, got it. And scale down by 4. X equals -1. Okay, now I want you to notice that we got x equals -1 both from the table, from the graph. We wrote down our solution, and now we just set these two equal, and we found x equals -1 from setting these two equal as well. And now all we would have to do is find the y that corresponds with that. Well, the good news is either equation will actually work. I'm going to go ahead and do it in both equations. So in the first equation, y equals 2 minus 2 by -1, and that's positive. So a negative times a negative makes positive, so 2 plus 2 is 4. And in the second one, if I put that -1 into the second one, 6 plus 2 by -1 is 6 minus 2, so that's also 4. So that means regardless of which equation we plug this x into, we'll still get the same thing. That's exactly what we intended to do here when we said the y is equal to the y. There it is showing up, yes? So even here, our x value, when x is -1, both equations have a y value of 4. Okay, and this is the last way. It's called substitution. So table where they match, graph where they meet, and equations where we set them equal. Let's look at example 4, breaking even. The cost to manufacture one certain type of computer is $200. But to keep the factory running, there's an additional cost of $12,000 for each day. These computers are sold for $500 a piece. Okay. Write an equation describing the daily cost to make these computers. Okay, where do we have? Here's a cost. This is a flat fee. It's the initial amount. And then it costs $200 per computer. So the cost is initially $12,000, but it's $200 each time they make a new computer. Uh-oh. C for cost, and I don't know. I'm going to go N for number of computers, because if you make 3 of them, then you just cost yourself $600. So it was 200 3 times. Daily cost. And N equals number of computers built. Okay, made, I guess. Write an equation that describes the money that is made selling these computers. Okay. That is revenue. It says they are sold for $500 a piece. So 500N, where R equals the revenue and N equals the number of computers. So here it's the number of computers built, and here it's the number of computers sold, but that's okay that they're the same. We're hoping that they're the same. Write these two equations as a system. Okay, so we have two equations working together to solve a problem. And revenue. Got it. So money going out and money coming in. Solve the system. All right, well, we're going to use the new way where we set these equal, so where the cost is equal to the revenue, and then we solve it. So you could also graph these or create a table of values. Okay, I'm gonna take away 200 n's from both sides. And then I'm going to scale everything down by 300. What does that make? 40? Yeah. Okay, but remember the solution to a system is two values, right? So if we find the revenue in this situation, the revenue would be 500 times 40. How much is that? 20 grand. And the cost to create 40 computers is $12,000 plus 200 times 40, 20 grand. Okay, so to build 40 computers in a day and sell 40 computers in a day, the cost would be 20 grand and you would make 20 grand. So you would have a zero balance. What does the solution mean in the context of this situation? This is called literally breaking even. Okay, so the money spent to make 40 computers is $20,000, and that's the same amount made on selling 40 computers. This is breaking even. Money out is the same as the money in. All right, let's take a look at example 5, getting an accurate answer. All right, it says, use the graph and table of values in order to find the solution to this system. Okay, I feel like we're going to have to do a similar thing where we rearrange these and write them as in y equals blah, blah, blah form. So let's just get started on that. The first one, maybe I'll write it over here. X plus 3y equals negative 1. I'm going to go ahead and subtract an x from both sides. And I'm going to scale everything down by 3. So y would equal, scale this down by 3. So negative x scaled down by 3, and scale 1 down by 3 minus 1/3. Okay, and I'm going to do the same thing for the second one. Let's see. Oh, but all I have to do is really scale down everything by 6. So in the second one, 3 scaled down by 6 is actually, okay, I'll just write it. It's a half, right? Simplified. Minus 7x scaled down by 6. Okay. Oh man, we're going to have some fractions, I feel like. I'm going to try using the graph, actually. Now that I've rewritten these, they look like they're ready to put into a calculator. Okay, so what did we have? For the first one, we had what? So make sure you're using this negative symbol right here, because if you use the subtraction symbol, it does not like it. So negative x divided by 3 minus 1/3. Got it? And then the second one was the equation 3/6 minus, okay, that numerator, Okay, I'm trying to make it, there we go. That numerator needs to be glued together. 7x, that whole thing is scaled down by 6. Okay, and now I'm going to go zoom, and I'm going to go down to standard, enter, and it's going to graph. Nice. Oh, I have no idea if that's right on or actually a little bit over. So I'm going to go second, calc, down to intersect, hit enter. Yes, yes, and guess, sure. Ah, I see. It's in repeating a repeating decimal. So we do know that x equals 1 where they intersect though. Okay, so this must be doable. Okay, let's do it quick. So that means good things. A couple of good things are happening. First, went ahead and did the graph first. Okay, looked a little bit like this. And they met here. And the answer said when x equals 1, y equals negative 0.666, so on and so forth. And now let's go ahead and make a table of values. It says they're going to match when x equals 1, so maybe this will be actually quite short. When x equals 0, this would be 0 minus a third, negative 1/3. When x is 0 in the second equation, we will get 1/2. Okay, and this equation, when x equals 1, we will have negative 1/3, take away a 1/3. Well, that is negative 2/3. And if we plug in 1 for this x value, oh boy, I have to write it out. So 3/6 take away, well, 7 by 1 is 7. 7/6 is negative 4/6, and simplified, that is negative 2/3. Whoa, it really did work out. So notice, okay, our solution is 1 and negative 2/3. Yeah? It says check our solution. So we're going to put those into the original, and we're going to make sure that they are truly equals. Okay, let's do that. So the x value is 1. 1 plus 3 by negative 2/3. Does that equal negative 1? All right, well, 3 of these is actually negative 2. 1 plus negative 2, does that equal negative 1? Yes. So it works in the first equation. Now we make sure that it works in both. This one, the second equation is 6 by y, so 6 by negative 2/3. Does that equal 3 take away 7 x's, which is 1? Okay. Well, 6 sets of negative 2 is negative 12. So this is negative 12/3. Does that equal 7 sets of 1 is 7. 3 minus 7. And I would say yes. This is saying negative 4 equals negative 4. So it checks out. It really is our solution to this system. Nice. Couple of remarks before we do our last example here. It is actually very challenging to get fraction answers without making any mistakes using a table and using a graph. So fraction solutions are harder to get right with tables and graphs. Just the way it is. I mean, it might have to get rounded, it might be you know, a little bit, it just, sometimes we can make mistakes. It's just a little bit harder. And then also the substitution method is perfect for dealing with something like this. Like if we have a precision problem, that's when equations come into play. That's when algebra comes into play. So it is a tool for being right and for being precise and accurate. So we use algebra. And here, we set the equations equal. And that is called substitution. Okay, so we would just set the two equations equal and solve it. But that is really what it's motivated for. In the last video, we will do a contextualized example so that we actually understand. So other than the cost and revenue, which was a good one too, it's important to break even, but we'll go ahead and do another one in order to go through the motions again.